really fast.
Okay, or you can give that to me and I'll bring your Math Excel up on my screen so that we're both looking at it. But
Okay.
if it's easier for you to go ahead and just log in and then look at the problems and we can, a lot of times, most algebra problems you can verbalize.
Yeah.
The only ones that are difficult to verbalize is if they're giving you a graph and they want you to interpret the graph.
Yeah.
In which case, then we'd need to be looking at something.
Okay. Well, I think this one I could verbalize.
Okay.
It says find a polynomial with real coefficients that have the given zeros of -1 and 3 minus 4i. So it's just two separate zeros.
How many zeros are there?
Well, I don't really know. My teacher was telling me that 3 minus 4i could count for two zeros.
It does, definitely.
Okay.
Imaginary solutions never come one at a time. They always come in pairs. So
Okay.
if this is one of the zeros, then we automatically know that that's another zero, the
Okay.
conjugate. In other words,
Okay.
whatever that sign in the middle is, change it and you have your other zero. So
Oh, okay.
those are the three zeros for the polynomial that we're looking at. What kind of polynomial is it? Is it a quadratic, a cubic, a quartic?
It's a cubic.
Correct, because cubics have three zeros.
Yeah.
Okay.
It gives me an equation here.
Well, what's one of the factors? If minus 1 is a 0, what's one of the factors?
X plus 1.
What's another factor?
X minus X minus, or 3 minus 4i.
And the third factor?
It's X minus 3 plus 4i.
Okay. In other words, if I told you that I had zeros at 2, 4, and 7, you would know the factors are x minus 2 times x minus 4 times x minus 7, right? That's how you get the factors.
Yeah.
Well, same thing when you have imaginary solutions or imaginary zeros. We're still going to do it exactly the same way, nothing different. Now, the algebra is a little tricky here. The first step would be to remove the parentheses. Okay, so this one, when I remove the parentheses, that minus 4i turns into a plus. And when I remove the parentheses over here, that turns into a minus. So those are our factors. If we multiply those three factors together, we'll have our polynomial. In other words, it's pretty much the reverse of factoring.
Yeah.
If I gave you a cubic polynomial and I said solve it, you'd do the whole process in reverse. Well, the best way to do this is to multiply the trinomial by the other trinomial.
Okay.
What do I get when I do that? I'm going to set the x plus 1 aside for just a moment because I'm still going to have to multiply the result by x plus 1, but okay, so x squared
minus 3x, and it's going to be minus 4 or 4ix,
okay.
And then it's going to be another minus 3x,
Okay.
And then it's going to be positive 9,
Okay.
And then it's going to be a positive 12i,
Okay.
And then 4ix
plus 4ix, right?
Yeah, positive. And then a negative 12i. And then a minus 16i squared.
Okay. I squareds can always be converted to real numbers. What's I squared equal to?
Negative 1.
Okay, so let's rewrite this and simplify it. We got only one x squared. We have a minus 3x, we have another minus 3x, and that's all the x's we have. So we have minus 6x.
Yeah.
Now we have a minus 4ix and a plus 4ix. So I can cross those out.
Okay.
I have a plus 12i and a minus 12i. I can cross those out.
Okay.
So I have plus 9. And then what's I squared equal to?
Negative 1.
So what's minus 16i squared equal to?
Positive 16.
Okay. Hold on a minute. Let me scroll down a little bit. Now we have x plus 1 times x squared minus 6x plus 25. Okay, so one more multiplication and we have our cubic polynomial.
Okay.
So what is it?
It's going to be x cubed minus 6x squared plus 25x plus x squared minus 6x plus 25.
Simplify. Incidentally, whenever you're doing these, you only have one of those terms and you only have one of those terms. So
Okay.
simplification comes from the middle.
Okay.
Okay, so I know there's only one x cubed. How many x squareds do we have in total?
Negative 5.
How many x's do we have in total?
25. Or, no, 19.
And how many numbers? We know that's the only number.
Yeah.
We only know that because there's no i's or I squareds in here. But even in the previous one, notice that we had a number there and we end up with a number there, a real number, because it had complex. So here's our function.
Okay.
In other words, if you, whoops, I didn't simplify it. Was that 19 or 19x? That was 19.
It's supposed to be 19x.
Yeah. Okay. So if they gave you this function and they said find the zeros, you would get back to the 3 zeros that you gave me, minus 1 and those 2 imaginary ones.
Okay.
Now, one thing that's worth knowing that you might not be aware of is that when you have imaginary zeros, they do not cross the x-axis. In other words, even though we had 3 zeros, it only crosses the x-axis once. Something like that.
Okay.
Because the 2 imaginary zeros are not x-intercepts. Notice if we take a simpler problem that has no x-intercepts. That is y equals x squared plus 1. Well, if you try to find the zeros of that, you get nothing but you get 2 imaginary zeros because you end up with x squared equal minus 1. So x is equal to plus or minus the square root of minus 1. So x is equal to plus or minus I. And so we have 2 zeros, but we don't have any x-intercepts. And that's the way it should be. Imaginary zeros do not produce intercepts. X-intercepts. Okay, what else do we have?
Okay, it says find the rational zeros, and then the other zeros of the polynomial function x cubed minus 43x plus 42. That is solve for f of x equals 0.
Okay.
And then it says to factor f of x into linear factors. And then it gives me three total options, and the first one's like there are only rational zeros, and then the second one is the rational zeros are blank and the other zeros are blank,
Okay.
and then the final ones there are no rational zeros.
Let's start out by trying to find a rational zero. We think there are three zeros, right? Because we have a cubic.
Yeah.
Well, imaginary zeros always come in pairs, and irrational zeros always come in pairs. In other words, that's an irrational zero.
Okay.
Okay, so if I find a square root of 3 minus square root of 3 is also going to be a 0. So when you have cubics, it's almost always you're going to have at least one rational zero. Now, finding it is not easy. People who think that the quadratics are difficult to solve with the quadratic formula, that's kindergarten stuff compared to this.
Really?
The rational factor theorem says that if I have a rational zero for this thing, its numerator is going to be a factor of the constant, and its denominator is going to be a factor of the coefficient of the highest term. Well, that's 1. So, let's talk about factors of 42. What are they? Let's list them all.
Let me see.
Way to do this, the way I like to do it, is start with that, and then cut this in half and double that.
Okay, so it's going to be, 21 and 2.
Now, I can't cut that in half anymore, but I can cut it in thirds. So try that, and triple this. Now 7 is a prime number. I can't do anything with 7. So I believe I have all of the rational factors.
Okay.
No, I don't. I can cut this 6 in half and double that. So there's 2 more factors.
Oh, true.
Now I'm done.
Okay.
I can cut 14 in half, but it doesn't give me 2 new factors.
Yeah.
Here's what the rational factor theorem says. Rational factor theorem says that the numerator can be that, or that, or this, and it's always plus or minus, because minus 7 times minus 7 also gives you 7.
Mm-hmm.
Let me erase. Hold on a minute. Let me just get rid of some of this stuff. And the last one is plus or minus 3. So those are our possible numerators.
Okay.
Our possible denominators are factors of 1.
The x to the third.
Yeah, the coefficient on that is 1. And our denominator are going to be all possible factors of that.
Okay.
So that makes this kind of easy. In other words, if this was something other than 1, let's say that my denominator could be plus or minus 1 or plus or minus 2. Now what I have to do is come up with all solutions. So I have to consider that as a possible factor, and that is a possible factor.
Okay.
In this problem, we only have one denominator, and that's plus or minus 1. So we don't need to consider that, but it's not always like that. Okay, so I can essentially say that my possible rational factors are these 1, 2, 3, 4, 5, 6, 7, 8 times 2. There are 16 possible rational factors. How do I figure out which one is it? Trial and error. That's the only way, unless you're allowed to use a calculator. This was not a calculator problem, correct?
No.
Okay. If they force you to do this by hand, you can take comfort in the fact that any test is only going to have one of these problems on it at most, because these are 20-minute problems.
Really?
Yep. And the only way I'm going to figure out which one is the rational factor is to try every one until I find one.
Okay.
Okay? Once I find one that works, well, now if I have one linear rational factor, I can divide it into that, and what's going to result is a quadratic. And once I get it down to a linear factor times a quadratic, I can use the quadratic formula. In other words, the goal is to get it down to linear factors and a quadratic. Well, how do we figure out if one of these solutions is the correct one? Well, we can do a few things. We can do synthetic substitution or synthetic division. I happen to like synthetic division. They're both the same thing. They work out the same way. The advantage of synthetic division is that when you find the answer, you have the remaining quadratic staring at you in the face.
Mm-hmm.
So you've done synthetic. They wouldn't be asking you this problem if they hadn't taught you synthetic division. So let's do synthetic division here. First of all, what goes across the top?
42.
The coefficients of this polynomial.
Oh, I thought you meant like in the little box to the
Not
left.
yet. Not yet. We'll get to that.
Yeah, no. Yeah, okay, I understand.
Across the top, we have to allow for every power of x, and we're missing an x squared from this thing. So I have to put a 0 there for that missing x squared. And then minus 43, and then plus 42. Now, what I'm going to put in the box are going to be each of these things. Okay? But generally, I start with the easiest numbers. In other words, it's just a lot of arithmetic at this point.
Yeah.
Okay? So let's start with 1. Let's try that. And we're just going to try 1, we're going to try minus 1, then we're going to try 2 and minus 2 and 3, and then 6, and then 7, and then 14, and then 21, and then 42.
Okay.
Okay? Although, it almost looks to me like 42 works. Let me think for a second. If I bring down the 1, I get 42, 1, 43, 1, yeah. I'm just in the interest of efficiency and time, I can tell that 42 works.
Really?
Yeah, I think so.
Okay.
What's the first step of the synthetic division here?
Just bring the 1 down.
Now what?
And you times the 42 by 1.
Now?
That is...
that's 42 times 42. No, 42 is not going to work. I don't know what I was thinking. In order for it to work, we have to end up with a 0 over here. Right?
Yeah, so
that's our goal, is we're going to keep trying these numbers until we get a 0. Well, I kind of got ahead of myself thinking 42 worked. I would never have started with 42. I would have started with 1, always. Just because the math is easier. Okay,
True.
so let's try that. Huh. Look what worked perfect. our first attempt. So
Okay.
at this point, we now have two factors of that polynomial. What's one of them?
0.
No, x minus 1. In other words, 1 is a 0 for this thing.
Okay.
If you put in 1 and do the math here, you get 1 minus 43 plus 42. That does equal to 0. Okay?
Okay.
So that's one of our linear factors. And the other factor has to be a quadratic. What is the quadratic? It right there. You're looking.
Okay. What is that, x cubed or is that x squared?
X squared. It's got to be a quadratic.
Okay.
Plus x.
Plus x minus 42.
And now the problem becomes fairly straightforward and simple. I can factor 42. If I can figure out how to scroll my page here, I'll do it. In other words, now quadratics are a piece of cake to deal with compared to cubics. That looks like it's going to be x minus 6 times x plus 7. So your three solutions are what? If all of them are equal to 0.
6 and negative 7.
Notice that all of those were on my list. 6, negative 7, positive 6, and positive 1 were all of the possible rational factors. So I could have started at 6 and it would have worked. I could have started at negative 7 and it would have worked. I would have gotten the same solution and it would have only taken me one trial. But had I started at 42 and tried both of those, no go. 21 wouldn't have worked, 2 wouldn't have worked, 14 wouldn't have worked, and 3 wouldn't have worked. So I could have wasted 15 minutes if I didn't happen to pick the correct one right off the get-go.
Yeah.
I'd still be working on this thing. So that's what I said, these are 20-minute problems. They aren't always. If you get lucky and find it on the first try, then it's fairly straightforward.
Okay, so would you say these are only rational zeros?
Yes. Let's talk about rational versus irrational. What's the difference?
I have no idea.
Rational number is a number that can be written as a fraction. So all whole numbers can be written as fraction. So all whole numbers are rational.
Okay.
3/2 is rational. 9/4 is rational. All of those can be written as fractions. What cannot be written as a fraction? Square root of 2, square root of 3, square root of 5. Any radical that is not a perfect square is an irrational number. There's no way to write that as a fraction. In fact, it's a never-ending decimal. You know, it goes on forever. It's like pi. Pi is also irrational. You cannot write pi as a fraction accurately. Accurately, you can't.
Yeah.
So that's the difference. And when you, like I said, you can get irrational solutions. Here, let me write, if I told you that x squared is equal to 2, well, take the square root of both sides and you get plus or minus square root of 2. Notice we have two irrational solutions to that problem.
Okay.
That's why I say irrational solutions come in pairs, just like imaginary solutions come in pairs. When they give you a cubic, it's hard to have nothing but imaginary and irrational solutions since they always come in pairs, right? So you almost always have to have at least one rational solution for a cubic. If I have a quartic, not true. In other words, if I have x to the 4th and a bunch of other stuff, I could have two irrational and two imaginary solutions, which leaves me no rational solutions, which makes it really tough to solve quartics because you might not have a rational solution. The
Yeah.
rational factor theorem merely says that if there is a rational solution, you can find it using that method that I used.
Okay.
But if there isn't, you're not going to find it, you know. And then I've never been taught what to do, how to solve it if there's no rational. Usually the case is you find one rational solution and then you reduce the rest of it to a quadratic, which you can always solve using the quadratic formula.
Okay. And right after it says the factorization of x, or I mean of f of x into linear factors is blank. So what would that mean? Like, would that mean like the whole
Those were the
equation?
3 linear factors we got,
Oh, okay.
right? Those are the factors. Those aren't the zeros. The zeros are +1, +6, and -7.
Okay.
The linear, that is a linear factor. That is a linear factor. That is a linear factor. Linear merely meaning the power of x is 1. If I ended up with a factor like that, that's a quadratic factor. In other words, if I ended up with something like this, but this is also called an irreducible quadratic. And in fact, if I was factoring this polynomial, this is where you stop. You don't take it all the way to its imaginary solution.
Okay.
You factor a polynomial down to its linear factors and irreducible quadratics. So this could be a final solution for, you know, if I multiplied these two together, I'd have a cubic polynomial, and this would be the 2 factors of that cubic polynomial.
Okay. All right. So the next question says find only the rational zeros of the following function of f of x equals x to the 4th plus 12x cubed minus 15x squared minus 24x plus 26.
This cannot be a problem that they want you to do by hand.
Yeah, I don't know. It says the rational zeros are blank, and then the other option is there are no rational zeros.
Well, the reason I say that they don't want you to do this by hand is because it would take too long.
Really?
Notice how many factors of 26 there are. 26 and 1, 13 and 2. I guess that's all of them. Yeah, let's give it a shot without a calculator. What I've found is the case when students give me these kind of problems is that they were meant to be done with a calculator.
Really?
Yeah, in other words, put that, I have a calculator on my computer that will give me the zeros. I don't know if you're familiar. Are you familiar with Wolfram Alpha?
No.
It's a terrific program to have on your calculator. I'll show you why. On your computer, excuse me. It's better than a calculator. Hold on a minute. I just have to figure out my computer to put both of these pages up at the same time. I'm going to put this, here, let me minimize my GoToMeeting. Okay, let me put this in, and I can put it in as x to the 4th plus 12x to the 3rd minus 15x squared. What's the rest of it? Minus 24x?
Minus 24x plus 26.
Okay. The beauty of Wolfram Alpha is that it tells you what you put in. If you have a TI-84, the TI-84 will not give you this feedback. But if you have a TI-Inspire, it will. or Wolfram Alpha also tells you what you input. And I can see that I put it in correctly. Okay? And it gives me all the zeros. Normally, it doesn't want to give me the zeros. Did I put it in correctly?
Let me see.
X to the fourth plus 12x cubed minus 15x squared minus 24x plus 26.
Yeah, that's it.
Well, this is the first time I've ever seen it not give the zeros automatically.
Really?
But you can see that it gives you the four factors right here.
Okay.
That one is irrational, that one's rational, that one's rational, and that one is irrational.
Okay, so the only ones are 1 and negative 13.
Are the only rational factor.
Okay.
And we could have discovered those. In other words, by using the technique, we knew our numerator. Let's go back and look at that technique again, because there are not that many factors of 26. But the possible numerators are plus or minus 26, plus or minus 1, plus or minus 13, and plus or minus 2. Possible denominators are plus or minus 1. So these are our possible, there's 8 potential rational factors. And I just have to keep trying them. And again, 1 would work. Okay?
Okay.
In other words, when I start with plus 1, it's going to work. And the only reason I know that is because I can see over here that x minus 1 was one of the factors. So I know 1 is a 0. Now, after I found 1, if I had to do this the hard way, I would start with 1, it would work, and then I would have a cubic remaining. Right?
Mm-hmm.
In other words, if I take away one of the linear factors, I'm left with 1 degree less of a polynomial. So I've got x minus 1 as one of my factors, and then the rest of it is going to be cubed. And then I have to do exactly the same thing with that cubic.
Yeah.
I have to find the possible rational factors of the cubic using the same technique. And I'm going to find the, what was the other one? 13 or?
Don't remember. Let's see.
It was negative.
Yeah.
Negative.
13.
Okay. So after I find the plus 1 and the negative 13, the hard way, then I've got x minus 1 times x plus 13, and what's left is going to be a quadratic. I can handle that quadratic easily, even if it's complex, even if she wants you to factor it. Typically,
Okay.
math says reduce it to linear factors and or irreducible quadratics. Irreducible meaning that it has nothing but imaginary solutions. Okay, so that's the way you do these problems. They're extremely tedious. It's a lot of trial and error. You don't dare make one mistake or you're going to get it wrong, and there's probably 20 steps to coming up with the solution.
Mm-hmm.
So that's why I say that typically when you get a problem like that, it's meant to be put into a calculator or a computer. And once you, what kind of calculator do you have, Alex?
TI-84, I think.
Okay. If you were to put that thing into your TI-84 and graph it,
Mm-hmm.
you can find the zeros because you know how to do that? Using the trace. In other words,
yeah.
there's an option for finding maximums, minimums, zeros, pick that and use the trace. And the way you have to do it is kind of like this. Let's say the function ends up looking like that. It's a quartic, so I have 1, 2, 3, 4. It's not going to look quite like that. It's going to look like this. A quartic can have at most 3 local extrema. That's a local maximum, that's a local minimum, that's a local maximum. I can only have 3 of those for a quartic. If I had a cubic, I could only have 2 of them. If I have a quadratic, I only have 1, the vertex. Now, and since we came up, I know what I was going to say. This is what your calculator looks like after you've graphed it. Next you push find the zeros, then you put it on trace, and you have to mark a spot to the left of that 0 and a spot to the right of that 0 using the trace button, and it'll tell you that point right there. Go over to this one, do the same thing. Mark a spot to the left of the intersection, to the right of the intersection, and it'll give you that spot right there.
Okay.
Now, since my Wolfram alpha already told us that there were 4 zeros, I must have drawn this thing wrong. It must be like this, because we have 2 more zeros right there. And you find those the same way as you find these zeros. You put the trace on the left, the right, ask it what that 0 is. Do the same thing there, and find that 0. So your calculator, you can find all 4 zeros, and you'll find 1, negative 13, square root of 2, and square root of minus 2. Or whatever those zeros that Wolfram alpha gave us were. Okay?
Okay.
I don't know what else to say about that problem. But what else you got?
All right. It says describe the end behavior of the given function of negative square root 3x cubed. It looks like a negative square root 3, and then like next to that is x cubed. So the x cubed isn't under the square root.
Like that.
And then it says plus 4x squared minus 3x plus 4.
What's it want you to do with this?
It's just asking for the end behaviors.
Okay.
If it's going to be like negative, negative, or like positive, negative.
End behavior is determined exclusively by the highest degree polynomial.
Okay.
You can cross those off. They have no effect on the end behavior.
Okay.
Okay. So what we want, end behavior means as x goes to infinity or negative infinity. So what I really am looking for is the limit of negative square root of 3x cubed as x goes to infinity. What does that go to? What is that limit? I know you haven't had limits yet, but you can kind of think of it. Plug in infinity for x. What do you get?
You get 3 infinity.
Negative square root of 3 infinity, which is the same as negative infinity.
Okay.
2 infinity is the same as infinity. Or infinity. The key is that as x goes to infinity, that goes to positive infinity, but there's this negative sign out here, which means it goes to negative infinity. Okay? That's the right-hand end behavior. The left-hand end behavior is as x goes to negative infinity. What happens to that whole thing?
It's just going to be negative or
positive. In other words,
positive.
What we're going to end up with is negative square root of 3 times negative infinity cubed. Well, when you cube a negative number, it stays negative, right? Cube negative 2 and it becomes negative 8. So if you cube negative infinity, you get negative infinity. But now we have two minus signs. So it results in a plus.
Okay.
So end behavior is determined strictly by the highest degree term. You can throw all the others away. And then just substitute infinity for x and see what you get.
Okay.
All right, you have some more end behavior problems. It might be worth doing at least one more.
Yeah. So the function for this one is going to be 2.61 x to the fourth minus
dot. I don't care what else there is.
Yeah.
Has nothing to do with the end behavior.
Okay.
So if I want the limit of this thing, as x goes to positive infinity, all the way to the right, what is it going to be?
Positive infinity.
And if I want the limit of that function as x goes to negative infinity, all the way to the left, what is it?
Positive infinity.
Yep. And what that kind of function would look like, it would be like this. That's a quartic. You know, there's three local extrema. Notice that as we go that way, all the way to infinity, I'm going to positive infinity up there. And as I go this way, all the way to negative infinity, I'm still going to positive infinity. As opposed to a function like this, a cubic, where as I go to positive infinity, it goes to positive infinity. As I go to negative infinity, it goes to negative infinity.
Okay.
Okay? All right, what else you got? Before I forget, Alex, can I get an email address for you and your mom?
Yeah, no worries.
What's your mom?
So, my mom's is ICB Denver at hotmail.com.
At what? Continental?
Hotmail.
Hotmail. Wow,
Yeah.
I wasn't even close, was I? That's good, because I wasn't sure how to spell continental. Okay,
Yeah.
and what's yours?
No, it's just Alex.
A-L-E-X?
Yeah, ALEX, and then a capital C, and then lowercase BOWDEN. So it says Alex C. Bowden.
Okay.
And then at gmail.com.
Okay. I need yours to send you the link for this recording, which my computer will take all night to process my online sessions today. But by tomorrow morning, it'll be processed and you'll be able to review the session if you want. It'll be in a YouTube file, so you can fast forward, rewind, pause if you want. And I need Mom's. I will send her the invoice for this session.
Okay.
Okay? And she can pay by either check or PayPal. If she has a PayPal account, it's far easier paying by PayPal.
Right.
But if she doesn't need to go to the trouble of opening one. She can just send me a check, and on the envelope I send her, my address will be on there. So.
Okay, yeah, I think I might actually have a PayPal that she might be able to transfer money in that I might be able to just use, but I don't know. I'll just ask her if she has one.
Okay. Or you can just wait. I will send her the invoice tomorrow, and then she can do whatever she wants. She'll have an account. She'll know how to do PayPal if she wants to do it by PayPal, or she can just send me a check. She'll have everything she needs.
Okay.
Okay? All right, back to your problems. We still have like 12 minutes.
Okay, so it says find the zeros of the function and their multiplicities.
Okay.
F of x equals x cubed minus 2x squared minus x plus 2.
All right. Now this is a special kind of cubic. We don't need to use the rational factor theorem here. I can solve this cubic by grouping.
Okay.
You remember grouping, or have they I'm sure they've taught it to you, because the first thing they teach people about cubics is if it can be solved by grouping, do so. It'll be far easier than the rational factor theorem. Okay. And the way you group it, or the reason it can be, is because I'll just do it and show you how to solve it by grouping. Okay?
Okay.
I'm going to rewrite it as x minus 2x squared in parentheses. And then I'm going to subtract, and I have to write that as x minus 2, notice, because I added the parentheses.
Mm-hmm.
In other words, when you rewrite it, make sure it does not change. It's the same function. And you can see that it is. In other words, if I take away those parentheses, I have minus x plus 2. Same thing I started with.
Mm-hmm.
Okay? Now, on the first set, I factor out an x, leaving 1 minus...
Oh, you wrote an x instead of an x cubed.
Thank you.
So now we could take out an x squared.
No wonder it wasn't working like I wanted it to.
Yeah, I was like, he's probably going to...
Thank you for catching that. Actually, here's what I wanted to do. I wanted to factor out an x squared, leaving that. Okay? And then over here, I don't need to factor out anything. Now, you're not used to factoring this like this, but you can factor out binomial terms. You don't always have to factor out a single thing like this. Notice how I can factor the rest of this. The rest of this, if I factor out the x minus 2, which is part of both terms, what am I left with?
X squared minus 1.
And that factors also. So now I have x minus 2 times what? That's difference of perfect squares. How does that factor? X minus 1 times x plus 1.
Okay.
Those are your three factors. Much, much easier if you can do it by grouping than doing it the hard way. Now, the reason I could do this by grouping is because the ratio of the coefficients of the first two terms were 1 over minus 2, right?
Mm-hmm.
And the ratio of the coefficients of the second two terms are 1 over, or minus 1 over 2. As long as those two ratios are the same, then you can solve it by grouping, always. In other words, even if I had something like the following, does this answer your question for this problem?
Let me enter it really fast.
Before I erase anything, I wanted to make sure we had answered the question.
Yeah, no worries.
Just wanted you to factor it.
It wanted me to find the zeros.
Okay.
So let's try. Let me
So
find
the
the
zeros are +2, +1, and -1. Okay. Let's change the problem slightly and put a 4 there and an 8 there and a 4 there. Now, I can still solve it by grouping because the ratio of these things is the same. In other words, the ratio of the coefficients are 4 over -2, which is the same as -8 over 4. So that means that it can be solved by grouping. Now, obviously, most of your cubic polynomials you're not going to be able to solve by grouping. I would say, if you run into 100 of them, only one will fit this criterion. Where,
Really?
how strange is it that I've got to have that ratio equal that ratio in order to solve it by grouping? If I change this last number to a 3, then I can't solve it by grouping.
Yeah.
Because those two ratios are no longer the same. And you'd have to solve this the hard way.
Okay.
Rational factor theorem way. But if they give you a cubic that can be solved by grouping, usually you're supposed to solve it by grouping.
Okay.
Okay? In other words, they mean for you to solve it by grouping. All right, what else you got?
I'm reading this problem, but it looks like it might take too long. Alright, so it says oh, this one looks crazy. I don't know if we should do this one.
I'll let you decide that.
I mean, like, the word, it has a lot of crazy numbers, and, like, it's a word problem, too. So, I mean, I don't really want to, like, put that on you in the last 5 minutes.
Okay, you got a shorter one?
I'm just kind of scrolling through the list, looking at them right now.
Well, that's right. You're getting them off the off the computer, aren't you? Yeah.
Yeah, yeah.
The word problem might not be as crazy as you think.
Do you want me to read it to you and see how?
Read it out loud. Yeah, we may.
Okay, so it says the number of bald eagles in a state during the winters from 1996 to 2002 can be modeled by the quartic function, and then it gives me an equation.
Go ahead.
And it says where x is the number of years since 1996, find the number of bald eagles in the state in the winter of 2000.
Okay. So what's the function?
It's negative 3.316 x to the fourth plus
Not
35.
not hard enough without giving you these kind of numbers. Okay, go ahead.
Yeah, right.
I know.
Plus 35.083 x cubed minus 95.395 x squared. And then plus 41.454x plus 178.498.
Okay. X is the number of years since 1996, right? So in 1997, what would x be?
Y plus 1.
No, x would be 1. X is the number of years since 1996.
Oh, okay.
So in 1996, how many bald eagles are there going to be?
0.
No? All the x's zero out, but we still have that amount right there.
Oh, okay.
So in 1996, there's 178 bald eagles.
Okay.
But they wanted to know in the year 2000, right?
Mm-hmm.
Well, that's 1, 2, 3, 4 years after 1996. If 1997 x is 1, 1998 x is 2, well, by 2000 x is 4. So the answer to the problem, plug in 4 for x and come up with a number. And that's how many bald eagles there are in the year 2000.
Okay.
And I'll let you do that.
Yeah. No worries about that. It's
Well,
fine.
there's probably a relatively easy way to do it. I don't know how familiar you are with your TI-84, but if you put in a function, a lot of times it will let you evaluate that function for a given value of x. In other words, just input this function into your calculator and then find how you come up with y given a value of x. In other words, let's call this f of x instead of y. Well, what we want is f of 4. Okay? And I will let you do that on your own and come up with a number. The number, it's not going to be much to me. But, yeah, you can either do it manually. In other words, you can just 4 to the 4th power, multiply it by that number, and just keep doing it and see what you get. But from all of these crazy numbers they're giving us here, my guess is that they really kind of want you to use that feature of the calculator, where you put in f of x, and then you can put in any value of x you want, and it'll tell you what that's equal to when x is equal to that value.
Okay.
Okay?
Yeah.
And
I had no idea
if you don't know how to do that, you know, if there's anything you don't know how to do on your calculator, go to YouTube.
Really?
Yep. YouTube will have a 5-minute video or a 2-minute video that tells you how to do anything you can do on the calculator. You just have to, you just have to know what you're doing. You might have to word it in a manner that could be difficult to word, but I'm not sure how I would word that. But just in passing, when you have stuff that you don't know how to do on your calculator, you can always find out from YouTube.
Really?
It's a great resource. Yes.
Yeah,
just
good to know.
In YouTube, let's say you wanted to do linear regression and you forgot how to do it. Well, go to YouTube and search for linear regression using a TI-84. And there'll be a dozen videos that'll show you exactly how to do linear regression.
Okay.
Okay? So you just have to know how to word the question right.
Okay.
All right. Alex, it's been fun dealing with all those quartics and cubics. And it's never fun, trust me. But we all have to go through it, I guess. So that's college algebra for you.
True.
Good luck on coming up with this number.
Yeah, no, I just typed it in. It was right, so that's good.
And yeah, the whole secret of this problem is knowing that x is 4 in the year 2000.
Yeah, no, I had no idea like how to even go about this, so that's good.
Okay.
All right, sounds good. I'll probably try online sessions in the future. Like this is easy.
You can always they're really easy to schedule, and all you need is 1 hour advance notice. And
okay.
I'll let you schedule one. So,
Okay, sounds good.
all right. Have a good evening. I'll talk to you later.
All right, sounds good. You too.